Hello everyone. Welcome to Module 8.3 of the GPU Teaching Kit. This lecture covers the tile boundary conditions part of the stencil parallel computation pattern. The objective of this lecture is for students to learn to write a tile 2D convolution kernel. As we will see, a tile 2D convolution kernel is a fairly straightforward extension from the tiled 1D convolution kernel we covered in the previous lecture. We'll be first introducing a 2D image data type that students will be using in their lab, and we'll be also giving students some API functions to make the manipulation of the images easier. We'll introduce the concept of constant caching for convolution masks. And then we would extend the concept of input tile size versus output tile size from 1D to 2D. And then we would introduce the concept of 2D thread to data index mapping, which is a fairly straightforward extension from the 1D thread to data index mapping we already introduced. And then we will handle boundary conditions in the 2D case. The students are going to be applying convolution to two-dimensional images in their lab. We're going to be using an image data type that is used by many real-world packages that process images. In a real-world package, it's oftentimes desirable to pad the images so that each row of these pixels will be of a multiple of the DRAM burst. For example, in the picture, we show that a 3x3 picture, but the DRAM burst will cover 4 pixels. So in a padded image representation, we will add a dummy pixel to make each row 4 pixels, so that each row will occupy an entire DRAM burst. With padding, each row will start at the DRAM burst boundary, and padding effectively adds columns into the original picture. And this is usually done, the padding is usually done automatically by the matrix allocation function. So when the package allocates a new memory for a new matrix, the padding is usually automatically done. And the number of elements after padding is called the pitch. And pitch usually corresponds to the DRAM burst boundary, and in some cases, page boundaries. And so the pitch can be different for different hardware because they correspond to the DRAM burst or page size of different hardware. In our example here, the height of the picture will be 3. The width of the picture will be 3. And we assume that there's only one channel that is a chromatic picture rather than an RGB picture. But in the real lab, students are going to have RGB 3 channels. And in this example, because we padded one element into each row, the pitch is 4. Continuing our example, once we padded the elements, we're effectively making each row longer. So the bottom of the picture shows the original matrix with 3x3, and we padded into a 3x4 picture. And then we take the picture and lay out in a linear order. So we see that now we have the padded elements at the end of each row. And then when we linearize the elements into linearized indices, we see that now we have to account for the additional elements. So the additional elements M3, M7, M11 are the padded elements, and this makes the remaining elements index bigger than what they were without padding. For example, the M21 element after padding is going to be 2 times pitch, which is 4 plus 1 equal to 9. Without padding, the linearized element for M21 should have been row times width plus column, which is 2 times 3 plus 1. So that would have been 7. So this padding affects the linear index for all the elements. That's why we wanted to make sure that we introduce the concept so that the code will make sense to the students. So in the host code, in the web GPU, we have already introduced the image matrix type. And the image matrix type is a struct of width, height, pitch, and channels. And these are the quantities that we already introduced in the previous slide. And then we have a pointer to the data. And this data is actually the padded array that contains the padded matrix for the image. We have provided a collection of API functions to make the manipulation of images easier for the students. So we have a image new and image import that can allocate memory for the image, and also to import the image from a file. And we can also delete an image, that is, it will deallocate the memory for that image. And for each image, we can get the width, the height, the number of channels, and the pitch of the image. And then we can get the image data from with the API function. So for simplicity, the pitch of all the matrices are said to be the same as the width times channels, so that there's no need for padding. And this makes the kernel simpler. And we're going to extract the image and pass it to the kernel so that the kernel function does not have to deal with all the additional width, height, channel, and pitch information inside the kernel. And all these things are done in the host code. Now that we have completed the background of the image data type, we can get into the design of the tiled 2D convolution kernel. In the host code, we also need to set the block dimensions. And this is a very simple extension of the one-dimensional case. Here, we need to set the block width to be 2 to the power. So this particular example assumes that we're going to set the block to be 16 threads by 16 threads. So in order to set the block size to be 16 by 16, if we're using a convolution mask of 5, we will be defining the output tile width to be 12, so that the block width will be output tile width plus 4, which is 16. And then, since we're declaring a 2-dimensional kernel, we're going to have a block dim set to be block width, and 1. And then finally, we're going to set the grid dimension to be the width of the image divided by the output tile width in the x dimension, and then the height of the image divided by the output tile width in the y dimension, and then 1. And the complexity is all about the ceiling function. So this gives us a fairly straightforward extension of setting the block and grid dimension as a simple extension from the one-dimensional case. Like in the previous lecture, we're going to be assuming design 2. So we're going to be using both input index and output index, assuming that the thread block is going to be large enough to have every thread to load an input element, and only some of the threads will participate in the calculation of the output element. The calculation of the output and input indices are also very simple extensions from the one-dimensional case. For the output indices, we're going to calculate both row index and column index for each thread. And this is calculated by skipping over all the output elements covered by the previous thread blocks, and then add the thread index into the index. So the number of output elements covered in the vertical direction by the previous thread blocks is block idx.y times the output tile width. And then we add the y-dimensional thread index into the row index. So this gives us the vertical direction index for the thread. And then we calculate the column index, which is horizontal direction index, by skipping over all the output elements covered by the previous blocks, and then we add the index, the x-dimensional index, into that index. Once we have the output indices, we can calculate the input indices by subtracting 2 from each of them. This is assuming that the mask width is 5. In general, we should be subtracting the mask width minus 1 from each of these indices. So in the picture, we show that whatever the output row index for thread 00 should be, the input index should be the output index minus 2. The next step is to load the input elements into the shared memory. As we will see, this is also a very simple extension from the one-dimensional case. The code we have here assumes only one channel, and the students will need to extend it into 3 channels. We will be testing for both the vertical direction and the horizontal direction whether the row index for the input and the column index for the input are within the valid range. If they both satisfy the condition, then the thread will load its corresponding input element into the shared memory. And the index that we'll be using is the row index times width plus the column index. This actually should have been pitch, but in all the data that we prepared, we will make the pitch the same as width, so that will be okay. If either the row input index or the column input index is out of the valid range, then the thread should be just loading a 0 value into the shared memory. And this corresponds to the case where the thread is attempting to load a ghost element into the shared memory. So when we load the data into the shared memory, we would just use the y index and y thread index and the x thread index to address the shared memory array element that will receive the input element. Like in the 1D case, some of the threads will not participate in the calculation of the output. So as we can see, we have a very simple test whether both the Y index, thread index, and the X thread index are within the output tile range. So if they're within the output tile range, then they will proceed to calculate the two-dimensional convolution between the input tile and the convolution mask. And we will come back to the usage of the M matrix here, but for the purpose of this slide, it's important to see that the 2D convolution is simply a very simple extension of the 1D convolution based on the shared memory. The students will need to write the kernel for a 3-channel RGB image. So we will have more details in the lab assignment. Now we will deal with more details for accessing the array M. Remember, M is the convolution mask array. The elements of M are the convolution coefficients that will be used in the inner product calculation. And when we calculate the output elements, all the output elements need to use M elements. And also M is not changed during the kernel execution. A very important behavior in accessing M is that all the threads in a thread block will be accessing M in exactly the same order in the inner product loop. This means that during the execution, the value of the M elements can easily be broadcast to all the threads in the thread block at every step of their inner product loop execution. Here is a review of the programmer view of the CUDA memories. In the bottom of the picture, we see that there's constant memory in the GPU, and it's read-only access by the kernel code. And this access can be very, very fast, about 5 clock cycles also with constant caching. This slide explains how we can place some of the variables for the kernel into the constant memory. The host code will still initialize the variables the same way as any other variables that need to be copied to the device. And we will just refer to one of these variables as SRC. And then the host needs to declare a constant memory variable, which we'll refer to as DST in the slide, to be used by the device. The important part is that after the declaration, we need to use CUDA main copy to symbol to copy the host variable SRC into the constant memory variable DST, and we need to specify the size. And this special CUDA MPI function tells the device that the variable will not be modified by the kernel and can be safely cached and for efficient use by the kernel code. So back to the convolution code, we can declare the mask array as a two-dimensional constant memory array by declaring it as with the keyword underscore underscore constant underscore underscore. And we mark that the M array as MC to remind ourselves that this is a constant memory array. And it's a statically declared array, so we can use a two-dimensional notation and declare it as kernel size by kernel size. And the next batch of code essentially just allocates and initializes the M elements as a host array. And then we use CUDA main copy to symbol to copy the elements of m dot elements into the MC array. And then the number of elements that, the number of bytes that we need to copy is kernel size times the size of float. After this CUDA main copy to symbol function, we can launch the kernel, the convolution kernel as what we did in the past. This concludes module 8.3 of the GPU teaching kit. Thank you.